Good evening, Matt.
Good evening.
Ready for a good day in chemistry? How was your weekend?
Yes, I am. It was pretty good. How's yours?
Yeah, I can't complain. It's busy, but progress is being made, so I can't complain too much.
It's good.
Mauricio, how are you?
I'm good, Tony. How about you?
Oh, not bad, not bad. Are you guys happy that everything is coming to a conclusion?
Yep.
I can't speak for everyone.
Yeah. We'll wait a little bit to let a couple more people slip in. Let's see. Mikey, did you get the yeast from Cole?
Yeah.
Yeah, I got halfway, well, not halfway home. I got up Kalinga Hill and then I remembered, I'm like, oh crap, I forgot to.
Oh no.
Yeah.
Yeah, Jessica texted me, so then I just texted Cole and we went and picked it up.
Cool. Yeah, that should it should salvage it. Did you use all the yeast?
We weren't sure exactly what to do with it, so we're just gonna ask you today because there were a couple different things.
Good, sounds good. We can wait after class, we'll do lab. So
Yeah.
okay. So you guys should have gotten an email with from me that is giving you guys a poll as to when you guys would like to take the exam. Did you guys receive that email?
Yeah, I saw it.
Mm-hmm.
The sooner you guys respond, the sooner I can narrow down those time windows. As of right now, I'm waiting for the exams to be delivered, but they haven't came in yet, so I'm a little worried. So we may have to have a backup plan for the exam, but I'm not worried about it too much. You'll have one more exam. It's a take-home test, so you guys can work together as a group. It'll be like 4 or 5 questions. They'll be challenging, but you guys should be okay overall. They're going to cover basically up to equilibrium, and hopefully today we'll finish up most of equilibrium. I know we have a little bit more to go on Wednesday, and Wednesday is going to be your last lecture. So after that, I'm just going to give you guys a whole bunch of notes for the future reference for the chapters that we are lacking. Okay. Are you guys there?
Yeah, sounds good.
I know it's a Monday,
Yeah.
Okay. So let's go ahead and get started. We'll see what we can get through. Are there any questions?
No.
I like it when there's no questions. Let me close this up. Did anybody do anything exciting and fun this weekend?
I just worked.
You just worked? Yeah, me too. Imagine that. Some days I envy those people that, you don't take work home with you, where
Yeah, that's the good thing about my job is I don't have to take it with me.
Yeah.
Once I clock out, I'm done.
Let's see. Okay. Give me 1 second. Okay, so I can't recall where we left off at. So we'll start here. Can you guys see my blue screen?
No.
No, not yet.
Well, if you guys didn't want to have lecture, you didn't have to kick me out of the classroom.
We'll never do that to you, Dr. Henry.
Oh, okay. Okay, so can you guys see my screen?
Yes.
Yeah.
Okay, good. Let's see. So I believe we briefly talked about acid-base dissociation constants. Yeah, no, maybe?
Yeah.
Sounds vaguely familiar.
Vaguely familiar. So just like everything else in equilibrium, it always is going to be exactly the same. You're always going to have your products over your reactants, right? You know that you're only going to be using aqueous solutions and gases when you're talking about equilibrium, okay? So you're not going to be using solids or liquids for your equation, right?
Right.
You look at this, Ka stands for the dissociation constant for an acid. And so this is the generic form for an acid, because an acid is, again, just a proton donor. So here you're donating the proton to water, which is acting as the base, okay? And so you're always going to get your products over your reactants. And in the case of a weak base, the same thing is going to happen. Here you have your base, and then a base is a proton acceptor. So then it's going to be receiving, okay? So then again, it's going to be your products over your reactant. Simple, right? The thing about this is that you can always say that when you have a weak acid and a weak base that are coming together, the equilibrium constant is going to be equal to the equilibrium or dissociation constant of the product of the acid and the base is going to be equal to that of water. Okay, and so then if you guys remember that, that's just going to be that concentration squared, so it'll be 10 to the minus 14. Okay, so knowing all of that, and you guys calculate the Ka for the dissociation of a 0.100 molar hypochlorous acid solution with an equilibrium hydrogen ion concentration of 2.38 times 10 to the minus 5. Okay, so what are we going to do? What does hypochlorous acid look like?
What?
What was that?
I have no
Hypochlorous.
idea.
Hypochlorous. Come on now, you don't tell me you forgot. Perfect, Mauricio. So Mauricio says it's HClO. And we know that's AQ. So we're reacting with liquid water. And we know the product is going to be, what are going to be the products? Remember, hypochlorous acid is a proton donor. So then what are going to be the products?
Hydronium ion.
The hydronium ion. And the conjugate base. Okay, so then what is going to be the equilibrium constant?
The equilibrium constant of the whole thing?
The equilibrium constant for dissociation. So what is going to be the equilibrium constant equation, I should say?
So it would be the concentration of H3O plus
Okay,
times. Oh, actually, the videos are cutting off the last one. Is that last one ClO liquid or?
here, I'll
No.
keep dragging. It's ClO aqueous.
Aqueous. So then times concentration of that.
Okay. Is that better?
Thank you.
You're welcome. Okay. Is that it?
No, then it would be over. It'd just be the concentrations of the other two times each. Do we include water?
Water is a liquid. Do we include water?
No.
Nope, we don't
Okay,
include
yeah.
water.
I forgot.
Old age, you know. I'm gonna start calling you grandma. Kayla.
Yeah, I mean, as long as it means I can retire, that's good with me.
Okay, so then that's what we do to sit there and calculate it. And again, this is at equilibrium, right? So if we know that at equilibrium, let's say we have our ice table. Getting ahead of myself here. Okay. So I stand for what again?
The initial
Okay. The C stands for,
change,
and the E stands for,
equilibrium.
okay. So initially, we have this much of this concentration of hypochlorous acid. The change is going to be represented as X. So in this case, so we're subtracting X. And then over here, since these guys are going to be subtracting from here, this is going to be generated on this side, X. But they also gave us the value of our hydronium ion at equilibrium, which is 2.38 times 10 to the minus 5 molar. Okay. So what do we know about the hydronium ion compared to the hypochlorite ion? What can we say?
Wouldn't the equilibrium be the same?
It would be exactly the same. That's right. Because we know that the number of moles for this is 1 to 1, so the concentration of this guy would be 1 to 1, right? Or exactly the same. Okay, so we know what X is, right? Because then X is going to be equal to just that concentration. So then we could just simply say that X equals 2.38 times 10 to the minus 6, or sorry, minus 5. Okay, molar. Now, if we look at this number here, and this here for at equilibrium should be 1.00 minus 2.38 times 10 to the minus 5. Okay. So if we compare this number to this number, we know that, let's do it like this, minus 0.000238. Okay, so if we add these together or subtract them, in this case, where would I draw my line for sig figs? Do you guys remember that?
The one with the least amount?
So right here,
I think so.
that is correct. Okay, so then we would use this number to round if we did the subtraction, and this guy would be what? 0.9999762. So, oops. Is that true?
Yeah, that's what I got on the calculator.
Okay, so if we did sig figs, we'd end up with just the same number. So we'd end up with 0.100, right? Is that true? After we round it using this number?
Yeah.
Okay, so after we round this number, we'd end up with the exact same number that we started out with. Okay, so this tells us if this number, if the concentration of our products is so low that it isn't going to affect that number, we can neglect it. We don't have to worry about it. Okay, and this number is so low that we can neglect it. We don't have to worry about it. Okay, so we can just kind of ignore this. We ignore because it's so small. Okay, so then if we plug these values in, then we'd end up with 2.38 times 10 to the minus 5 squared. Right, since these concentrations are exactly the same, over 0.100. And that's going to give us our Ka. Okay, so if we go ahead and plug that in,
I got 5.66 times 10 to the negative 9th.
Okay. Okay, so then that would be our Ka. Simple? Yeah,
Yeah.
no, maybe?
Yes.
Okay, so let's do the one below it. Calculate the Kb for 0.100 molar nitrate solution with an equilibrium hydroxide concentration of 1.50 times 10 to the minus 6. So what is that chemical equation going to look like?
Is it NO2 negative 1?
NO2 negative 1. Aqueous.
Plus H2O?
That's liquid. We're going to get who's going to be the proton donor?
Nitrite?
Is there a proton there?
Oh no. It would be the water.
Okay, the water is going to be the proton donor.
So it'd be HNO2.
And we know that this is a weak acid. Nitrous acid, so it's going to want to stay together. Plus hydroxide. Okay, so what is the Kb going to look like?
Should be the concentration of the HNO2 times the concentration of hydroxide. And then that would be over the concentration of nitrite.
Oops. Okay. So we go ahead and do the ice table. So what can we write where?
Well, we have the initial for the nitrite, which is 0.1 molar. And we also have the equilibrium for hydroxide.
Okay,
And that would be the same as the nitric acid too.
that is correct. So we know again, this change is going to be X here. So we're saying this is going to be minus X. Okay, we know the value of X. So is that number so small that it's not going to have an impact on this, or is it going to, do we need to take it into consideration?
It's so small that it's not going to have an impact.
Okay, so we can ignore this guy. Okay, so then we could say, room KB equals 1.50 times 10 to the minus 6 squared over 0.100.
And I got 2.25 times 10 to the negative 11th.
2.25 times 10 to the negative 11. Okay, sounds good to me. Questions, concerns, Cash? Kool-Aid? Okay, can I erase? Or do you guys need a second?
I'm good.
Okay. Okay. So when you're working with acid and bases, we can go through that whole process and use the ice table, right? So you're going to either identify the contributing hydroxide ion, or you're going to identify the contributing hydrogen ion or hydronium ion, which is the same thing as the hydrogen ion. You're going to write the balance equation. You're also going to write the equilibrium equation, which is that's your Ka equation. And then you're going to use the ice table to sit there and organize your data. So the 5% rule is basically looking at whether or not that number is small enough to have an impact or not. So the rule is basically if the answer you're going to get is going to be 5% or less, then it's not going to have an impact. If it's greater than 5%, it's going to have an impact, and you need to sit there and calculate the actual X. And so you're going to use a quadratic formula or something along those lines. Okay. Good so far? Okay. So when we talk about polyprotic acids are basically acids that can donate more than one hydronium ion or hydrogen ion. Okay, and I'll show you an example of that here in a second. And so in that case, the dissociation is going to be calculated solely by the highest or that strongest acid. Okay, and usually that is your first Ka, because that's going to be the fastest one that's going to happen. So that's going to be the most abundant, and the other ones are going to have very little impact on it because the numbers are going to be so much smaller. And I'll show you what I mean by that in a second. Okay. Okay, so this is just basically showing you that process. So if you have this general equation here, you'd write out your equilibrium. You write out the dissociation equation. You make sure it's balanced. Then you write out your equilibrium equation, and then you just do the ice table. Okay, and you plug everything in, you solve for X. Same thing in the case for a weak base, exactly the same thing. Okay, questions, concerns, Cash, Kool-Aid?
Will you go back to that last slide just for a quick second? One before this.
Okay.
Okay. Thank you.
No problem. Okay. So pH calculation for a weak acid. Calculate the pH for a 0.00180 molar formic acid, which is HCOOH solution with a Ka of 1.80 times 10 to the minus 4. Okay, so what are we going to do? First thing is what?
Write the chemical equation.
Write the chemical equation. Okay, so the chemical equation would be
Should be the formic acid plus water.
okay. Who's going to be the donor? Who's going to be the acceptor?
Water's the donor, right? Uh,
Okay, let me give you a hint. Formic acid. Acids are always proton donors.
right, yeah.
Okay.
I was thinking that it would be H2CO, but
The water is going to be the acceptor, so then it's going to be H3O plus. Thank you. Okay, so this is our equation, our chemical equation. Is it balanced? Actually, it should be written like this. Is it balanced?
I think
looks-
so.
Yeah, it looks like it.
Yes, it's balanced.
Balanced. Okay, so then what am I going to do next?
Do the ice table.
Ice table. Okay. So what are we going to do? Fill out the ice table.
Well, for the initial, it's going to be 0.00180 molar and 0 for the product side.
Okay. Okay. Then what?
We have a question though. Don't like if you already have Ka, do you still have to do the ice table though?
Yeah, because we're looking for the concentration of the hydronium ion, right? That's how we calculate our pH.
Oh, okay.
So we're looking to solve for X in a sense, right?
Yeah.
Okay, so then our change is going to be,
Well, for the initial, it'd be minus X. And
Okay.
for the product side, it'd just be plus X.
okay. Okay, and we know that those are going to be exactly the same. And then so at equilibrium, we're going to get 1,8 minus X. And this guy's just going to be X, and this guy's going to be X. So then our equation is going to be K is going to equal what?
X times X squared over
X squared. Okay.
over 0.00180 minus X.
And to solve for x, wouldn't you put in Ka is 1.80 times 10 to the negative 4?
That's right. Okay. So then I just solve for X.
Yeah.
So can I neglect this number or do we know?
Wait, what was the question?
Can I neglect this X? Is that going to affect our number or not? Or do we know?
I don't think we know.
Yeah, well, we don't know, but you can kind of look at the number that we're getting here to kind of gauge, right? And so this definitely was going to affect it based upon the size, more than likely. So I would say work it completely out. So if we go, was that 1.8 times so we get 3.24 times 10 to the minus 7. Minus 1.8 times 10 to the minus 4 x. We're going to bring these both over to the other side. So we'll get x squared minus, x squared plus 1.80 times 10 to the minus 4 x plus, minus 3.24 times 10 to the minus 7. Okay, so then you guys remember the link to plug it into the quadratic formula?
Yeah, I have it saved.
So let's see, let's light this up. Okay, so we have 3.2. Oops. Sorry. 1.8 and then e to the minus 4. And then this is minus 3.24 e to the minus 7. Calculate. Okay, so we know that our x can't be a negative value. So then x is going to equal 0.0000 0.486. And that's molar. Okay, so then how will we calculate our pH? Since we know that this is going to equal the concentration of our acid.
It would just be the negative log of that, right?
That's right. So we'll go equals negative log of 0.00486.
We got a 2.313.
Okay. Piece of cake.
Sure.
Yeah.
Strawberry with chocolate frosting.
More like carrot cakes is the worst kind.
I like carrot cake too.
It's all right.
Which one do you like more though, Dr. Henry?
What was that?
Strawberry with chocolate frosting or carrot cake?
Oh, I like strawberry with chocolate frosting.
Strawberry.
Much better.
Mm.
Yeah, don't let that leak out though. I'm sure there's
Okay.
people that are willing to pay a pretty penny for that one.
See.
Okay. Let's see. Okay, you guys got that? Is that clear?
Yeah.
Got it.
Okay. Okay, clear. Now we can do exactly the same thing, working the other way around with a base. I'm not going to do this for you because there's a strong possibility that you guys may see something exactly like this on the exam. So I want you guys to sit there and work good on your own. Also wanted to give you guys some files. I can't remember which ones. So I think I gave you all equilibrium files. Everybody has all of the equilibrium files, yes or no?
I'm pretty sure I have them all.
Okay. And then I'm gonna throw in thermal. I'm just gonna give you all the rest. Okay. It's in the chat window. You should be able to download them. Yeah, I'll take care of that for you, Mauricio, as well. So give me a second. Wrong class. So does it feel good to be going in the home stretch?
Yeah.
Yeah, my math finals this Wednesday, and then this is my last class.
Are you walking this year?
No, my sister keeps trying to convince me to go too, but I'm like, it's just gonna be so boring.
You should walk. You don't want to look back and sit there and say, man, I should have walked.
I'm gonna graduate from university with a bachelor's. I'll walk then.
I believe in walking at every point you can walk.
Well, you sound like my grandma. She's still trying to tell me the same thing. I
Yeah.
don't know. I just don't want to walk. I don't know.
Okay. So here, for this question here, it says calculate the pH of 0.02 times 10, I'm sorry, 0.0220 molar benzoic acid solution with the Ka equal to 6.40 times 10 to the minus 5. So how would I go about doing that?
You would first write the balanced equation.
Okay, so I'm going to be lazy and I'm going to say, call it benzoic acid. I'm just going to put an H here and put a B here. Plus and we know that the product is going to be H3O plus benzoate. Okay. So
And
then
you-
we're going to do what?
Then you would just do the ice table.
Okay. We know we're starting off with 0.0220 molar. We're going to get a change of X. We're going to end up with 0.022 molar. This guy's going to be X and X at equilibrium, starting off at 0 initially. And then we're going to end up with just X down here, and this should be 0.22 minus X. Okay, piece of cake. So then what am I going to do with that?
You would just plug into the equation.
Okay, we
So
plug in our equation.
it would be x squared over 0.0220 minus x equals 6.40 times 10 to the negative fifth.
Okay. Okay. So go ahead and solve for X. We'll get X squared equals So that's 1.41 times 10 to the minus 6 minus 6.40 times 10 to the minus 5. So then we get x squared should be x squared, oops, plus, gosh, it's just not wanting to behave. 6.4 times 10 to the minus 5 x minus 1.41 times 10 to the negative 6. And then we plug it into our equation, quadratic equation, and then we'll let the work be done for us. So negative 1.41 e minus 6. Calculate. So again, we know that x is only going to be a positive number, so 0.00116 molar. Okay, and then what do we use this for?
To calculate the pH, you just take the negative log of it.
Okay, so pH is just going to equal the negative log. Oops.
And I got 2.94.
Okay. Piece of cake.
Yeah. So
Okay.
the equations for Ka and Kb are the same. It's just one's for acid and one's for base.
That is correct. Yeah, and the thing is that at the end of the day, you're gonna have the general equation is going to be exactly the same. The only thing that you're going to be changing is like the type of chemical equation that you're doing. And so equilibrium is always going to be exactly the same. It's always going to be products over your reactant, right? And so you have to figure out your equation, products over your reaction. So equilibrium for acids is just a special case, and that's it. So it's no different than anything else. Okay?
Okay.
Okay. Can I erase?
Yeah. I mean, at least I'm good.
Okay. Okay, good, good. Let's see. Okay. Okay, so again, I'm not going to go ahead and do these. I'm going to kind of skip ahead to get us ahead. So just kind of work on some of these problems on your own, work out the ICE table and go through that process. Okay. Again, the hardest thing is always just setting up the equation. Once you get the equation set up, everything kind of falls into place. Always remember, first thing you want to do is write your chemical equation, and you can write it generically for an acid and base. It tends to work out unless you have a polyprotic acid, which again, I'm getting to right now. Okay.
Okay.
Okay. Okay. So, but before we get to the polyprotic acid, we're going to talk about the hydrolyzation of salt solutions. Okay. So when we're working with a strong acid and a strong base, the endpoint, or the point where you reach that neutrality, right, is going to be a pH of 7. Okay, because you end up with water and salt. Okay. So in the case of a weak acid and a strong base, or a strong acid and a weak base, your endpoint isn't going to be at 7. It's going to either be above 7 or it's going to be below 7, depending on the conjugate weak acid or weak base. So when you're titrating a strong acid with a weak base, basically meaning you have a solution that is a strong acid and you're dropping in a weak base, the solution is going to be acidic. So then you're going to have a pH that is going to be less than 7. If you're titrating a weak acid with a strong base, that solution is going to be basic because you're titrating with a strong base. So you're always going to be over 7. Okay. So what do I mean by that? So strong acid and a strong base, the equivalency is going to always be at pH of 7. Weak acid, strong base, your pH is always going to be above 7. If I have a weak base and a strong acid, where's my equivalency going to be?
Below 7?
Below 7. Okay. Piece of cake?
Yeah.
Yes.
Okay. Okay, so now we're going to talk about the effects of salts. So now that you've kind of know that general thing, we kind of have to just think about the equation and what's going to be happening under the different circumstances, right? So determine a pH effect of a solution with sodium hydroxide dissolved in water. We know that hydroxides are going to be strong acids. Strong bases. So what would we expect this to be? What we expect the pH to be if we're putting sodium hydroxide in water?
Would it be neutral?
Nope.
Is it a basic solution?
It's going to be a basic solution, right? Because you're putting a strong base in water. So we know pH of water is 7. So you don't have anything to neutralize that strong base. So you know it's going to be above 7, right?
Oh, yeah.
Okay. Now what about determine the pH effects of a solution with hydrochloric acid dissolved in water? We know that hydrochloric acid, is that a strong acid or a weak acid?
A strong acid?
We know it's a strong acid. So what's going to be that case?
Strong.
What was that?
Acid.
It's going to be acidic, right? Okay. So determine the pH effect of a solution with sodium chloride dissolved in water.
Neutral.
That one is going to be neutral. Yep. And the way you kind of have to look at this is because if we have NaCl, aqueous, plus H2O, who's going to be your proton donor? In this
Water.
case,
The water.
the water is going to be a proton donor. So in theory, you're going to end up with something like this, right? But in reality, because if you're donating, you'll be donating to the HCl. We know that this is a strong acid and it dissociates instantaneously, right? So this guy will never really exist, right? So you're never going to end up with that component. And because of that, it's going to dissociate immediately. So then your H plus and your OH minuses are really going to just balance out, right? And then us plus Cl. Sorry. Na plus. Okay. And then you're just going to basically end up with water, right?
Yeah.
Okay. So you're going to end up with a neutral case. What about in the case of the pH effects of a solution with barium sulfate dissolved in water? Okay, so let's write it out. We have barium sulfate. Who's going to be the donor? Who's going to be the proton donor?
Would it be the water?
The water again. So in this case, in theory, you should get but what do we know about sulfuric acid? Is that a strong acid or would it be a weak acid? And what do we know about strong acids? What do they do immediately?
Dissipate.
They dissociate. So in this case, this guy is just going to dissociate when it's in solution. So you're just going to end up with your 2H plus or H3O. Sorry. Plus SO4. 2 minus. So everything is going to be dissociated. And so
So
You're gonna
what
have-
if you left with water? So it's neutral.
there should be two, actually there should be 2 waters there. I mean 2 hydroxides. So you'll have this guy and that guy. So it'll be exactly the same. So it'll be neutral. That's right. Okay. So what about in the case of determining the pH effect of a solution of sodium acetate dissolved in water? the same thing, sodium acetate.
Yeah, that's what I was trying to do in my head right now. I wasn't sure if that was right.
No, you're right.
Because the water would be the proton donor, right? And then it would
Right.
make acetic acid, but it won't last long.
Well, will it last long? So what do we know about carbon acids? Are they strong acids or are they weak acids?
Oh, it's a weak acid.
It's a weak acid, so it's gonna last, right? So that means that you're gonna have these guys stand together. So you're gonna have more of this present than anything else. So is that gonna be it's gonna be an acid, base, or neutral?
Would it be a base?
That's right. So it's gonna be a basic solution. Okay. What about this last case? We have ammonium chloride plus H2O Okay, who's the proton donor?
The water?
Not in this case.
It would be the ammonium chloride.
The ammonium would be, right? So, because this guy's going to dissociate into just NH
Oh,
or plus. So then it's going to want to get rid of that plus. So then we'll end up with okay. So is this guy going to be acidic, basic, or neutral?
Basic.
Nope, not basic. What do we have present?
Neutral. Hydrogen ion. Yeah.
Okay, so what would that mean? Would that mean it'd be basic if you have a lot of those present compared to, you see any hydroxides there?
No.
So would it be acidic or basic?
acidic.
Okay, you guys get that?
Yeah.
Okay. Okay, clear. Oops. Okay, so when we talk about polyprotic acid, got ahead. Okay, there we go. Sure. Okay, so polyprotic acids are acids that are able to lose more than one, or able to donate more than one hydrogen ion. Okay, so like for example, we have sulfuric acid. Sulfuric acid is H2SO4. So if we put that with water, we'll end up with HSO4. SO4 minus plus hydronium ion. And then we're able to sit there and lose the second one, right? So each one is dictated by a different pH constant. Oops. Okay, so this first reaction is going to have a different pH, a different Ka than this guy. So it's going to have a different equilibrium constant than the second reaction. Okay, the first reaction is always going to have the higher value. Okay, so since this is a strong reaction, the first reaction is pretty much going to dictate, okay, because you're going to get most of your hydroxides coming from that first reaction, or your hydronium ions coming from that first reaction. And then your second reaction is going to give you a little bit more, okay? So let me show you another example. Do you guys kind of understand that so far? So this guy is going to be, the first one is going to be a stronger, and then the second one is going to be a weaker, and then the third one, if there's a third one, it's going to be even weaker, okay? Okay, so like I said, this here is the first ionization. So in the case of the first ionization, this guy's going to have a very large Ka associated with it. The second ionization, getting rid of that second hydrogen ion, that one is going to have a smaller than that first. Okay, so you're going to notice the size change. You guys understand that? You see that?
Yeah.
Lena?
Yes.
To be honest, kind of. My brain's like dozed off.
Okay. Okay. So let me give you another example or a problem here. So write the dissociation equation for a phosphoric acid, a polyprotic acid. Note, use the equilibrium arrows. Calculate the pH of 0.17 molar phosphoric acid solution with a pKa A1, so that's for the first reaction, being 7.5 times 10 to the minus 3. Ka A2 is going to be 6.2 times 10 to the minus 8. And Ka3 is going to be 4.8 times 10 to the minus 13. Okay, so which Ka is bigger? 1, 2, or 3?
One
Okay,
looks the largest.
so 1 is larger, right? So then if we sit there and write the equation for 1, so we have, what is the chemical equation for, or chemical formula for phosphoric acid?
H3PO4.
H3PO4. Okay, if we're doing a dissociation with water, what are we going to get?
Would you have hydronium?
Hydronium ion and
And H2PO4.
minus, right? Since we lost 1 plus. Okay, so that would be the first reaction. The second reaction would be starting with that H2PO4 minus reacting with water. Then we're going to yield what?
Hydronium.
Okay, hydronium ion
And then we have HPO4. Negative.
HPO4. And that's going to be 2 negative, right?
Yes.
Okay. And then the third reaction would be HPO4, 2 negative. Plus water. Hydronium ion. Oops. Okay. So if we go ahead and calculate this, we wanted to calculate the pH for the phosphoric acid. So the first reaction we have 0.74. Let me take a step back. So we'd set up our ice table, right? For the first reaction, we go ICE. So we'll have 0.174 or, oops. And that's for H3PO4. And then for H3O and H2PO4 minus, we're going to have zero initial. Then for the change, we're going to have X, and this guy's going to be minus X. So this guy is going to be 0.174 minus X. And then that's X. And so we'd solve for, we set up our equation and solve for X. So our Ka is going to equal K1 I know, does it feel like a math class yet?
Oh yeah. It feels like I'm taking 2 math classes this semester.
And you're like, man, I didn't think I would ever use any of that stuff that we learned in algebra. Okay, so we plug in our values. We have x squared. So in this case, we're going to assume that since this is a very strong reaction, relatively speaking, so we know that it's going to be pushing it in this direction mostly. So we're going to assume that we're just going to start off with that value, right? So we'll have 0.174 molar, right? And let's see here. So if we solve for our x values, we'll get x squared. Yeah, sorry, and that's going to be equal to 7.5 times 10 to the minus 3. And so then we'll get x squared times 7.5 times 10 to the minus 3. Times 0.174. Okay, so we get x squared equals 1.305 times 10 to the minus 3.
And I got x equals 0.036.
Okay. Okay, so we can take that number and sit there and check the 5% rule. So divide that by our original number that we have for this value here, that 1.74. Okay. So 0.312. Yeah, so that would be a significant value. So we'd probably have to go back and solve it for the whole thing. So we have to put in that minus x value here, so. Oops. Control-Z. Minus X. .54 times 10 to the minus 3 X. So bring these guys all over to the other side. X squared minus, I'm sorry, plus 7.54. I mean, 7.5 times 10 to the minus 3 X minus 1.305 times 10 to the minus 3. Okay, so we plug that into our quadratic formula. Guess we weren't too far off, but the number is X equals 3, I'm sorry, X equals 0.0326, and that's molar. So if we calculate the pH of that, so you get a pH of 1.49. Okay, so we could calculate the how much more hydronium ions that these guys will generate, but this value, since this value is so much lower, really all you need to do is calculate this, because these guys are going to add very, very little to that concentration. Okay, most of it is going to be in that very first dissociation. Does that make sense?
Yeah. So you would just have to do it with the first Ka.
That's right. Okay. Questions? Concerns?
No.
Bitcoin? Okay. Okay, so we'll stop here and we'll pick this back up on Thursday. I mean on Tuesday. I mean on Wednesday. That other day that you guys meet.
Is there going to be a lab tonight?
Just to go over your your drink. On Wednesday, you'll have your last lab, and it's going to be a electrochemistry lab.
And what are the stuff we're going to need for that, the lab on Wednesday?
So there are going to be 3 solutions. You're going to need your metals. You're going to need your battery, and you're going to need your voltometer, and then you're going to need your clamps that you've made for the lights with the LEDs.
Oh, okay.
Okay. I can't remember the solutions off the top of my head. I remember one of them is I think copper gluconate. It'll be a nice blue color. So that's one of your solutions, but I can't remember all the rest of them. Okay. Okay, so I'll see you guys in lab.
Yeah.
What do we need for that?
For
For today?
So today you will need, so last week you guys did the spark, right? So this time you're going to be doing the bentonite. Okay, so you're going to add the bentonite to your wine. You're going to sample it, and then you're going to make sure that you're getting nice fermentation, and then you're going to add the bentonite. Okay.
But we're meeting in lab.
What was that?
We're meeting in lab.
Yeah, we're going to meet in lab because there are going to be some other people coming in.
Okay.
For the morning class. Okay, so I'll see you guys there.
See you.
Okay, see you soon. Bye-bye.